Everyone, we are Group 3 and will be presenting on the topic Motion Mamba, efficient long sequence motion generation. To start, let's understand what human motion generation involves. Essentially, it's creating realistic 3D human motion based on given conditions, like a text description asking for a character to walk or jump. The output typically involves generating the precise angles for each joint in human skeleton over time, bringing a virtual character to life. The main goal is to make these virtual characters move in a way that truly mimics real human motion. This means the generated movement needs to actually reflect the input, feel natural, and correctly perform the desired actions. Achieving this is quite challenging because human movement is incredibly complex. Over time, researchers have explored several primary approaches models built around autoencoders, GANs, autoregressive models, and diffusion models. While these methods have advanced the field, each comes with difficulties. Autoencoders models struggle with very detailed descriptions. GAN-based models face training challenges, particularly in conditional tasks. Diffusion-based models, despite strong performance, have limitations. Firstly, they exhibit difficulty generating long motion sequences efficiently, often requiring substantial computational resources. Furthermore, transformer architecture commonly used aren't inherently designed for temporal sequences. Second, the efficiency of inference, the speed at which motion is generated, is constrained. This is negatively impacted by the attention mechanism's tendency to scale quadratically with sequence length, resulting in less efficient generation, especially for longer movements. These challenges highlight the need for new approaches that can handle long-range dependencies efficiently. This is where state space models or SSMs have recently gained renewed interest. Modern versions of SSMs stand out due to their ability to effectively capture long-range dependencies, significantly improved with parallel training techniques. This has led to various SSM-based methodologies such as LSSL, S4, DSS, and S4D. These methods are designed to process sequential data with a focus on modeling long-range relationships, often using near-linear computational strategies like the Mamba architecture. This marks a significant step for sequence tasks, including motion generation. However, adapting standard selective state space models for motion generation presents challenges. SSMs were not originally designed for sensitive motion details needed for accurate temporal representation, and there are complexities in aggregating latent space information suitable for human pose data. In response to these challenges, a novel motion generation architecture has been developed, tailored for long-term sequences and computational efficiency. This innovation is embodied in the Motion Mamba model, presented as a simple yet potent approach. The Motion Mamba framework introduces a pioneering diffusion-based generating system. It incorporates two key SSM-oriented components. First is the hierarchical temporal Mamba (HTM). This component is designed to process motion frames sequentially using hierarchical scanning to capture temporal dependencies at various levels, enhancing motion consistency. Second, the bidirectional spatial Mamba (BSM). This block analyzes the latent skeleton representation bidirectionally to maintain information flow and strengthen the capacity for precise motion generation. The Motion Mamba framework introduces an approach that strikes an exceptional trade-off between accuracy and efficiency. This figure shows the overall architecture of the Motion Mamba model architecture. It's a diffusion system with an encoder-decoder. Key parts are the HTM block for smooth motion over time and the bidirectional spatial Mamba for accurate body poses. These work together to generate realistic 3D human motion.
So in this section, we'll be talking about the foundational models used for the architecture of Motion Mamba, which are SSM and Mamba. So, for understanding a SSM, we would first take this problem which is related to the differential equation, which says that in a state there are some bunnies, and the number of population of bunnies uh, proportional to number of bunnies at that time by some proportional constant lambda. So, what we can do here is we can convert this problem of the state of the system into a mathematical problem, which can be written with the help of differential equation as dB by dt is equal to lambda bt. With this help of mathematical expression, we can solve this state of system problem. So, what we get from here is that differential equation can be used to model the state of the system. So now moving towards state space model, first we would like to understand what is state space. So it's just like a differential equation, state space can help you to represent a problem mathematically by defining some systems possible states like t is equal to 0, there are 5 bunnies. So you can further progress to find the number of bunnies at particular times of t. So, what are space-based models now? So, SSM models are used to describe the states which were defined in the state space and make some prediction on that with the help of their described states. Uh, how this this SSM works is that it takes a continuous input sequence and give you an output continuous equation, just like differential equation which work on continuous function. So, what the basis of SSM model is that it assumes that for any dynamic system, even for such as an object moving in 3D space, we can predict its further states with the help of just two equations. And the two equations are named as a state equation and an output equation, and which are defined as such. So, by solving this equation, we can predict the state of the system based on the observed data at any further time. So one note we should make already clear here is that the equation we defined here are actually a time invariant and linear. Linear, as you can see that it's ax plus by, and they are time invariant because for any time t, no matter what time t this equation two are you solving, the a, b, c, d are constant. So the equation can be visualized in form of this image provided as for the initial input is multiplied by matrix B and matrix T, while the input multiplied by matrix T is directly poured into the output, while the matrix when the input is multiplied by matrix B, it's summed with matrix A multiplied by the input state. That's what you define here, that matrix is multiplied by matrix B and matrix T. Uh, now the problem is how to train this state space model. So as we talked about earlier, the state space model takes an continuous input sequence. But the problem is we already talk in terms about data and samples, and they are actually discrete values, not continuous values. So what we have to do is we have to discretize our system. So how do we discretize our system? So by discretizing our system, we means that we will not provide it input as h of t, but rather we would provide it an input of h of 0, h of 1, h of 2, and h of t, based on which each will give us output as y of 0, y of 1, y of 2. So we can do that with the help of a method defined earlier known as Euler's method. So how does Euler method work is that first we would again define that differential equation which we used for an initial problem, and by some high school calculus, we know that a limit when this h tends to 0, we can define this as derivative of that function. And by moving the denominator and moving this negative term right side, we get this expression. And by just substituting b dash t from this number one equation, we get this number three equation. And as you can see, we have already removed this dB by dt term, and it's replaced by d bt plus delta. So by assuming this delta, means fixing this delta, we can find the value of b at any time t. So similarly, what we do before, we can do it for the state equation in SSM. So this was the same step as second step in previous, and this state space equation. And when we substitute this value, we get some amazing results. We get for h and t, means the state is multiplied by the matrix I plus del a, and input is multiplied by del b. So we can rewrite this I plus del is A dash and B dash. So we have successfully converted our continuous system to a discrete system. which equation are look like this. And as you can see in output equation, we have removed the uh, b dot xk term because we assume that d is just an skip connection. So in the original paper, instead of using Euler method for converting continuous to discretized system, they used a different method known as zero order hold. And the value of a dash b dash they carries like this instead of a plus del a. Also, when we previously said we can assume a value of delta and find the value of b at discrete times. So for model, we actually use delta as a learning parameter. Now we can simply, when we have discretize our system, we can simply put the time step values in the equation. Now, what interesting is that this is very similar to similar equations we were getting for RNN. So this is just like we can predict the next state of the system by using just the previous state and the current input. So this xk goes to hk and hk minus 1 goes to hk to provide output yk. So similarly as RN, we have unfolded this SSM. Now we have learned how to train our model and how to represent it. Now the problem lies it's not good for training because as you can see it's a sequential model, and when given large input, the weight would get very small and the model won't be able to train. So and another problem is that it's sequential, so it's not parallelizable and train time is very large. So what we can do for the second problem to making it parallelizable is that we can use a different version of state space model, which is convolutional mode. So how we get the idea of convolutional representation is that we again write the two equations for time step 0, 1, 2, and k. And when we are doing this, we see a strange pattern. Like for output y naught, we see b bar matrix is multiplied with x naught x0. Similarly, here b bar is multiplied by x1, and a bar b bar is multiplied with x naught. Similarly, here b bar with x2, a bar b bar x0. So what we are seeing is that as we move towards older input, the a bar matrix is multiplied, and for yk, as we can see, a bar is to the power k. So what we gain from here is that this all a to the power k, b to the power k, this all matrices are constant. So we can actually calculate this beforehand, even before the training starts. And that group of the parameters we calculate is called a kernel. We already pre-calculated before the training and directly use it during the training. Now, how can this help is parallelization is that its kernel is a constant value and can be applied to each token individually. As you can see here, the yk does not depend on hk minus 1 anymore. It just depend on the all the initial input. Now this is how the kernel works. Kernel is multiplied with adding padding, and as you can see, this is moving forward, but actually all the three kernels are applied at the same time, and we get the output at the same time. So now we have successfully made two versions of SSM, convolutional recurrent, and we are able to train it. We are able to parallelize the training. So uh, uh, now what we will do, we will use both the versions to create a modified version of SSM, which we call LSSL, a linear state space layer. And how this work is, we will use a convolutional for the training part because it can be parallelizable and lead to faster training. And we will use a recurrent version for the testing part because recurrent for any nth token, it will only consume constant memory for calculating the inference, as it does depend on the previous input and the current input and the previous state. Now, as we said earlier, there were two problems. One for the training part, and the other was because the for using larger input, we could lose the previous information. So now we will talk about the importance of matrix A. As we know, the matrix A is multiplied by previous state to get the new state. So what matrix A does, it captures the information from the previous state to build the new state. So that shows how important it is. So we need to be very careful while modeling the matrix A because it's the one responsible for passing the information of the states throughout the network. So how can we modify the matrix A to solve our problem of long dependency. So what we can do is that we can use something called hippo theory, stated by author. So what is hippo theory is that it's very similar to what we call Fourier transformation, which is used to precisely mimic an input function with the help of a sinusoidal function. But in hippo theory, instead of sinusoidal function, we use legendary polynomials, which just look like this. And so, hippo theory helps us to build a matrix in such a way that it approximate all the input signals seen so far in a vector coefficient. So now there is just one difference between Fourier transformation and hippo theory. Why we didn't use Fourier and used hippo? Because we don't completely mimic the input signal, but we build a very precise. The recent signal are built more precisely, while the older signals are decayed exponentially, which help in computation very much and faster training. So how this do is that let's say this x naught is the input signal, and as you can the recent part is this, and it has successfully reconstructed this part. But the previous input is not as very well reconstructed and has some decay in it. But the information is still preserved, like the minimum is here and the maximum is here. So this is how hippo works, and this is how hippo matrix look. It is just a lower triangular matrix with all the upper part of diagonal zeros. And previously we modified our SSM to SSL, and now we have by using hippo theory we have modified it to structure space model. So the we successfully solved the problems of how to train that, and the two further and we weren't able to train it properly because there was a node correlation. We also solved that by using convolution, and we also solved that long dependency problem. And now we have successfully modified till S4 level. Now, so even after getting such a good model, what led to Mamba? So author describes two tasks on which SSM cannot perform. So for one is called a selective copying. What is mean that let's say there's a comment in a Twitter and we say to remove some words from it and just provide as the keyword the most important word. uh, and the vanilla system or even the S4 can't do it. Why it can't do it? Because it isn't aware of the content it's been provided. Means it doesn't matter if you provided a one sentence, one paragraph, or a full page. It's individually take a token and work on it. There is no content awareness between each other SSMs of the word they are doing. Also, the second problem is the induction head, which works like teaching a child. So if I say that give me a box after the black, so it can look back and the a block bit after black box was the blue box and give us the answer blue box. It can't do it. Means it can't recall the previous history because it's the similar reason because there is no content awareness between the input we are passing it. So. What we can do is we can further modify the S4 to selective SSM. So how we can apply selectivity to SSM? So the way it works is, as we know, the matrix B and matrix D were multiplied with the input. As we ignore the matrix D as a skip connection, the only matrix B is left. So we can modify this matrix B according to the input we get. So usually we get input as VLD, where V is the batch size, like one sentence. L is the number of tokens in. So let's say there were 5 tokens, and these are dimension means the length of the dimension of the embedding of one token. Like one token has been embedded in 4 vectors, so D will be 4. And we modified this whole previous S4 to new S6, which we, with the addition of selection, because now matrix B is not constant, as we stated earlier as a note that it was time invariant and linear. So it's still linear, but it's not time variant as now the matrix is modified. Now, what problem happened by this modification? The problem happened is that we solved the problem of selectivity, but the previous problem of parallelism training has come again, because what we were doing, we were calculate the kernel beforehand before the training, but we now can't do this because A, B, and C are not constant; they depend upon the input, so we can't calculate the kernel beforehand. So so now we have lost our privilege over the parallelized training. So instead, what and how we can proceed further is that The problem is occurring because of the scan operation. The scan operation is the one which happen in the state equation. To tell what it really means, let's say you are told to calculate, find a prefix sum array of this array. So what is prefix sum array? Is it just the number in the array will represent the sum of all the numbers below it. So you can find the value here 15 by just using the previous state and the current input, like 6 plus 9. So it's very similar to how our SSM works. We can define the new state by using the current input and the previous state, h naught into a was our input, important matrix, and x1 is our input, which can be multiplied by v, which now depends on the input, and we can get the h1. So now the problem with this kind of operation is that it's linear. That's why which due to which the we have to wait for the previous input. We have to wait for the happening of h naught to calculate for the h1, and we are losing the parallelization here. So can we make this operation parallelizable? So the answer is yes. We can make this operation parallelizable, and how it's done is with the help of parallel scan algorithm. So how this happen is that to get the gist of it, what happen is that first this two pairs of some are calculated. Let's say first we will calculate 9 plus 6, it will give us 15. Then we'll calculate 7 plus 10, 17, 8 plus 10, 15. Now we get a second array with 15, 17, and 15. Now forget the original array. Now this new array is our original array. So now we will again take two pairs in this. So we were having 15, 17, and 15. So take that 15 and 17, we again get 32. So as you can see, this 32 we have already gotten with the help of parallelizable training. So what good comes from this is that these operations are constant, and the depth you will reach will be log n. So depending upon how much pair you take it, you can take two or you can take three, like 9 and 7 and 10 and 7. In this case, 6 and 8 will be left uncomputed. So for that, we use this sweep up operation, which is defined here. In case you are taking two, it's not necessary. So now our time complexity has been reduced from of n to of n by t, where t represents the number of parallel threads. So if one you are doing at a time, as previous it was still of n. So now we have again come to back our S6 model with preserving our parallelizable. So now let's make our SSM much more efficient, because it's not still a par with what we were before with parallel training. So what we can do is we can utilize uh, the weakness of the GPU. So the way GPU works is that it has two memories, DRAM and SRAM, and all the computation happens in an SRAM, and DRAM is you can think of like storage space. So whatever computation results come in SRAM are stored in the DRAM. So GPU is a very fast calculator, but a very poor copy cater. Something like that. So what happens is that the SRAM calculation are in terabytes, while this copying operation is in only gigabytes. So how to exploit this weakness? So what we can do is we can do something like kernel fusion. Like instead of doing computation copying, we can skip the copying part and directly do computation to computation. And when the final result can be directly copied. As you can see again here, we do computation, write results, calculation too. We can skip that middle part of writing that result. So with this, we are saving this relatively slow part and doing this SRAM on which GPU is better. This is known as kernel fusion. So one more thing which can exploit about the same thing is that whenever you write your model in PyTorch or TensorFlow, your whole model is converted into this computational graph. Where during forward propagating, this delta I by delta, del D by del A, and these values are find out, which are used in the back propagation. So when your y actually is calculated and subtracted from the y predict, and your loss is back propagated, use this value to see how much should your learning parameter be adjusted. So the problem here is that whenever you forward pass, you store this value in the DRAM, so that they can be used again during your backward pass. Now the problem is you are when you are calculating this in the SRAM, you are for during forward pass you are copying it in the DRAM, this amount to one copying operation. Then when you are back propagating, you are again copying from DRAM to SRAM. This amount to two copy operation. So this lead to very inefficiency. So instead, what author suggested is that during forward computation, we calculate these values for the sake of getting y actual, but we don't store them. We just forgot them, and during back propagation, we just again calculate them in the SRAM. So what we are getting, we are only doing one. We are not doing the two times copy operation, and we are utilizing its real ability in the SRAM because GP is better at computation which we are using. We are just computing again and again, and this recomputation is very negligible to the amount what would have cost for recopying that. So all this modification after S6. So first we learn how to train the model, then how to by discretizing a system, and then how to train our model faster, and how to apply selectivity, more upgradation to X6. Now improving further selective, further efficiency, and now we have finally reached to Mama block. So this is how Mama block looks like. It gives an input, gets the embedding, passes through convolution, so that every token have some of their feature mixed with each other, because selective SSM work individually on a token, and the group of Mama blocks is known as Mamba, as just how a group of encoder and decoder have to form a transformer. So now let's talk about motion diffusion model. This paper uses motion diffusion model for generating realistic human motion sequences. It uses diffusion model on the latent space instead of directly applying it on raw motion data. So, firstly, let's understand what is diffusion model. A diffusion model is a generative approach where we randomly sample a Gaussian noise from Gaussian distribution and gradually denoise it iteratively to get structured data. We start from Gaussian noise, as you can see from XT, and iteratively denoise it bit by bit to get to the structured data X naught. So in motion generation, we want to synthesize realistic motion sequence, but we cannot directly apply it on the raw data which we get as input, as it is very complex and it would be highly computational for the model to learn it. So instead, we use a VAE which compresses the input data which we get into a small latent vector, and then we apply diffusion model to learn it to generate this low dimensional latent space vector instead of applying it on the input data which we get. So now the question arises that how the model knows what to make from that Gaussian noise. So in here we use conditioning C to control what to generate by using the diffusion model. The paper C could be any text description or action label, and the paper uses a clip architecture which converts a sentence into a vector of into a vector, and model uses this vector as a conditioning vector to deionize the Gaussian noise. It predicts the latent vector using the time t and condition c. And now finally, the full motion generation full motion generation process is as follows. We give an input condition C, which is a text or action or any other thing, and we use clip architecture on this C to convert this into a vector, and then we sample a Gaussian noise of size latent vector, and using this conditional conditional deionizer with the condition which we got from the clip architecture, we gradually refine the Gaussian noise over t steps to get our structured data. And after we get this structured data, which is a latent space vector z, we send it through the decoder, which generates the actual motion sequence.
So now comes our Motion Mamba. So Motion Mamba basically utilizes a denoising unit architecture, which is distinguished for its effectiveness in modeling the continuous temporal sequences of motion frames. So why they are using unit architecture is basically unit is good for working on sequence of images that change over time, which is in our case as we are modeling a 3D model, 3D motion model. The denoiser, denoted by E theta, comprises n blocks, including encoder E1n and decoder D1n. As you can see here, this part is our encoder part, This is our mixer part, which I will come later on. And this is our decoder part. Additionally, the architecture is enhanced with the transformer-based attention mixer block M, designed to augment the model's ability to capture complex temporal dynamics. So this is what is talking about the mixer block. So basically, why we are using this mixer block is basically helps Motion Mamba understand which moments in time are important and how they connect. So it can basically make smart predictions about motion. And in this mixer block, we are using that uh, query key value thing only, which we use in attention and transformer. So this is our E theta X, which is our denoiser model consisting of encoder E1 to En, mixer block, and decoder D1 to Dn. So given that selective operations have significantly lower computational complexity compared to attention-based methods, we have increased the number of scans to achieve higher quality generations. So as you can see here, we are using k equal to 2n minus 1 scans for the encoder 1, and for next encoder E2 we will use 2n minus 3 scans, and we will go on in the En encoder we will use only 1 scan. Thereby, a novel aspect of a model is the introduction of a hierarchical scan strategy characterized by a sequence of scan numbers. As you can see, there are different layers, and in each layer we are doing different number of scans. This sequence specifies the number of scans allocated to each layer in descending order of complexity. So for first we will do 2n minus 1, then 2n minus 3, and it will have the most complexity, and this the least complexity. This hierarchical scanning approach ensures that processing capabilities are evenly distributed throughout the encoder-decoder architecture. So what is saying that we are going from 2n minus 1 to 1 scan, then a mixer, and then we will follow the same procedure in opposite direction. First from k equal to 1 scan, then 3, then to 2n minus 1. Within this structured framework, each denoiser is equipped with a specialized hierarchical temporal Mamba HTM block, which we'll talk in upcoming slides, which serves to augment the model's ability to process temporal information effectively. So basically, what HTM do is it is used to model temporal dependencies across time steps. So this is our our this block consists of an encoder. Each block consists of HTM block and a BSM block. So now coming to the hierarchical temporal Mamba, the HTM block processes compressed latent representation denoted as Z with the dimensions TBZ, of which procedure shown in algorithm 1. So as you can see that what we require is Z vector with dimensions TBC. The input Z is subjected to a linear projection layer producing transform representations X and Z with dimension E. So now why we are using this linear projection layer is nothing but a neural network layer, and we are using this because as you know that in SSM block it expects an input in a certain dimensions to align with our A and B, which we will use in SSM. And also we, as we are in encoder, we are in decoder we might do downsampling and upsampling. Now the next step utilizes a hierarchically structured set of scans k equal to s2n minus 1. This is like for any encoder, this is the number of scan it will do. So like you can see, this z was passed to the linear projection layer, which give us xz, the dimension tbe. Now what was this tb? It's the t means the temporal dimensions, basically number of frames in that video which we have taken. B is the batch size and C is the channel size. Now it converts our C to E, the linear projection layer, and K is the number of scan which we will do here. And these are our memory matrices which are required in our SSM. Each sub now in conjunction with the corresponding series of memory matrices A1 to AK, which I told earlier. Each sub-SSM scan first applies a 1D convolution to X, resulting in X dash O. As you can see, we are doing the scans this number of times. It's basically a k. And for for each scan, what we'll do is first we will pass the x to a convolutional layer, one convolutional 1D. Why we are doing this convolution is because it provides local content before applying SSM. And it what will do is it will convert this and it will convert into same dimension only, TBE x dash o, but it will capture the local content. Now x dash o is then linearly projected to derive b naught, c naught, and delta naught. So this x naught is given passed to a linear projection layer, which will give b naught, c naught, and delta naught, which are further used in SSM, which I have explained its procedure in previous slides. Now the delta naught, what we'll do is used for transforming a naught to a naught dash and b naught to b naught dash using using this delta naught we are transforming a naught and b naught to a naught dash and a naught bar and b naught bar. Yeah. Then what we'll do, it will pass this x dash o to the SSM with AI and it will result in an OI. I've explained this SSM, what is done in SSM and basically its architecture in previous slides. Now, um, after us executing a sequence of SSM scans, a set of outputs O1OK is compiled. This collection is subsequently aggregated via linear projection to obtain the final outputs of the HTM block. Okay, so now what we'll do is um, we have obtained O1 to OK, the case number of scans we have done. And what we'll do is aggregate this. Aggregate means convert it into a single vector, and then we'll pass it to a linear projection layer, and it will result in giving us ZHTM with dimension TBE, so is required. And then we will return this ZHTM. Now coming to the bidirectional spatial Mamba. In the bidirectional spatial Mamba block focuses on enhancing latent representation learning through a novel approach of dimension rearrangement and bidirectional scanning. This is important, the dimension rearrangement, because now we are not working on temporal dependency but spatial dependencies. So, so the first step is what we do is a TBC only. What we'll do is rearrange the CBT, because now we are working on channel size, not on temporal dependencies. And like what we'll do is we'll take pixel 1, then go to pixel 2, and that each pixel is not a single pixel, it converts all of its values. Basically it's a vector which consists of all of that pixel values in our time range, all of the values that I've taken, and that would be a single vector of pixel 1. Then pixel 2 is also all its value for different time steps, uh, and that would be a vector with the values for different time steps, and that will pixel 2 and similarly pixel 3 and so on. Initially it alters the original input dimension from TBC to CBT, like I said, because we're working on spatial dependencies, so that's why effectively swapping a temporal dimension. After this rearrangement, the input, now denoted z dash, undergoes a linear projection after normalization, resulting in dimension x and z of size e. So what we'll doing is passing the z dash to this and norm, and it will normalize this and return z, return a vector z dash, which is a normalized version of previous vector. And then we pass this to a linear projection layer, which will give us CBE, converting the temporal dimension to E, temporal size to E. The process involves bidirectional scanning of the latent channel dimension A naught bar and B naught bar, where X is subjected to a 1D convolutional yielding X dash O for both forward and backward directions. So like its name suggests, bidirection, what we'll go is we'll go forward and backward, or from starting from, let's say, pixel 1 to pixel n, then pixel n to pixel 1, so that we just not model it based on the starting pixel 1, but also from the ending to the beginning. So what we'll do is first pass this x into con1d, and which will give us x dash o, and then we will pass this x dash o into a linear projection layer, which will give us b naught, c naught, delta naught, essential for SSM. and this delta naught will be used to transform A naught to A naught bar and B naught to B naught bar, and we'll pass this to the SSM, and this will result in an output Y naught. The final output token sequence ZL is computed by gating and summing the phi forward and Y backward output with Z. This component is engineered to decode the structure latent skeleton by analyzing data from both forward and reverse viewpoints. So now what we do is we pass this Y forward and Y backward. These are basically outputs of the SSM for forward and backward, and this Z. Now what gate and sum means is basically our output from this is gate 1 in Y forward plus gate 2 Y backward. Now gate is basically, you can say, sigmoid of uh, Z plus in Z into weights, and the gate 1 plus gate 2 must be equal to 1. So this is what with the output of gate and sum, and then we will just do rearrange and rearrange CB2 back to TBC, and we will return that. Now this is a its main objective is to ensure the seamless continuous information flow, thereby substantially enhancing the model's ability to generate accurate motion. Like we are doing both forward and backward, so that we know how each pixel is dependent on other more effectively. Now this is achieved through maintenance of a dense information exchange, the information exchange which is critical for the model's performance.
Good evening, sir. I'm Pranjal. So for this slide, we have taken Motion Mamba is evaluated on two prominent text-to-motion synthesis benchmark datasets. The first dataset is human ML3D. So specifically, this dataset consists of 14,616 motions, with each motion accompanied by three textual descriptions and culminating into 44,970 scripts. It spans a wide range of actions such as exercising, dancing, and acrobatics, presenting a rich motion language corpus. So actually, in human ML3 dataset, we have mm, a lot of motions with three text descriptions, and it's culminated into 44,970 scripts, and it spans a lot of motions like exercising, dancing, and all. The second dataset is KitML. It consists of 3,911 motions paired with 6,278 textual descriptions, serving as a compact yet effective benchmark for evaluation of motion synthesis model. In this, we have less motions but a lot of textual descriptions, which is like compact but effective. So the evaluation metrics we are choosing is the first generational quality paper implemented on freshet inception distance FID to quantify the realism and diversity to motion generated by model. The second is multi-model distance, that is called as distance. It is used to measure the distance between motions, and text assesses the motion text alignment. The third is diversity metric. We use the diversity metric to measure motion diversity, which calculates variance in features extracted from the motion. And the last is multimodality, also referred as a modality. It assesses the diversity within generated motion, sharing the same text description. Okay, so we have the comparative results. The first is tested on human ML3D. So we can take like firstly the precision of R is really good. It almost matches the real data, and FID is significantly better than like a lot of methods like motion diffusion MDM. The distance is really close to the real data, and diversity exceeds the real data. We can see it's 9.871 versus the 9.503 in real data. Only one thing is not like good. The M modality, it's slightly lower than MDM, but like it's still really competitive. Okay, for the like now the results that are tested on KTML model. The R here is also very close to real data. It's 0.419 versus 0.424. The FID is second best after real data, and diversity almost matches the real data. But here are two weaknesses this time. The distance is slightly worse than real. It's 3.021 versus 2.788. And M modality is also lower.
So I'm Kushal, and I would be talking about the ablation study. So our ablation study begins with long sequence motion generation. We introduced a new dataset called Human ML 3D LS, focusing on motion sequences longer than 190 frames. When evaluated, Motion Mamba significantly outperformed other diffusion-based models. The key advantage here is our model's ability to capture long range dependencies effectively using state space modeling, making it well suited for extended motion sequences. Coming on to the next slide. Next, we tested the impact of hierarchical scan ordering in the hierarchical temporal Mamba block. We noticed a slight performance boost by reversing the scan order from lowest to higher levels, as it better captured the temporal motion density in lower level frames. Then, by increasing the number of scans in a hierarchical design, for example, using a scan sequence like 8421, we achieved further improvements in performances. This confirms the benefit of allocating more computation to layers, capturing finer motion details. Now, here we evaluated different scan directions in the bidirectional spatial Mamba block. Single direction scans provided only minimal improvements. However, using block-based bidirectional scanning significantly enhanced performance by allowing the model to capture spatial information in both forward and reverse directions. The bidirectional approach enables better information exchange across the latent skeleton, improving the model's capacity to generate smoother and more accurate motion sequences. Now, if we talk about the inference time, inference time is a major bottleneck for most diffusion-based models due to their sequential nature. Motion Mamba addresses this by leveraging the Mamba block and a lightweight architecture. Compared to the MLD model, which requires 0.217 seconds per sample, Motion Mamba is about 4 times faster, making it practical for real-time motion, generating without compromising output quality. So, summarizing all everything, Motion Mamba introduces a novel approach for long sequence efficient human motion generation. It's the first model to successfully incorporate the Mamba framework into this domain. Our architecture leverages HTM for temporal modeling and BSM for spatial alignment, achieving up to 50% better FID scores and significantly faster inference compared to the existing transformer-based diffusion model. This this demonstrates both the effectiveness and efficiency of our system. Thank you for your attention.